happens to the radius? Does it increase or does it remain the same?
A constriction is decrease, like
Okay.
squeezing, yes. So, what I written on board was capital R, resistance to blood flow, is inversely proportional to 1 over little r radius to the 4th power. And so, yeah, I actually do want to talk about that concept a little more now, because that is the next slide. So with that vasoconstriction of vessel radius, in particular for arterials, this occurs during a sympathetic response to increased blood pressure. Let's look at the physiology behind this. On the left there, we see what usually happens. You're having a good day, everything's fine. There's no power outage where you live. Parasympathetic on. I know some of this may be affected. So parasympathetic on. And what that does is, what I show is you're blocking the sympathetic. So when you do that, that sympathetic tone is down. Blood vessels tend to be more relaxed and vasodilated. I'll just put VD for vasodilate. The systemic effect we observe is a moderate drop in blood pressure. Okay? That's the basic idea. In a stressful situation, parasympathetic off. So that is removing the sympathetic block, and that nerve can fire more. Remove. Sympathetic block. So you're going to increase that sympathetic tone, as we like to call it. Increase SYM tone. It's like a volume knob. You're just turning it on louder. You fire more neurotransmitter onto the tunica media, and that causes the smooth muscles to contract, and you constrict the lumen, vasoconstriction. VC. The effect is to increase blood pressure systemically. That's usually what you observe. This is a system-wide effect. If you have a half sheet, if you didn't grab one, but on your half sheet, number 1, for a sympathetic response, SYM response. Half sheet number 1. That first blank and then that second blank. The first blank is, well, if you excite the sympathetic, what happens? Constrict or dilate. And then as a result of that, fill in the second blank. Does that increase or decrease BP? So really quick, fill that in. Boom, boom. SNS is sympathetic nervous system. If you excite the sympathetic, that's kind of what I said here.
Okay.
So what happens? Boom, boom. That's all I'm going for. To excite the sympathetic, I mean, I say it a different way here. There's a million ways to say the same thing. Turn that off. You're removing the sympathetic block. That's the same way as saying, I'm excited. So the concept is the sympathetic nervous system will constrict and increase blood pressure. That having been said, let's talk about the reverse. let's turn on the sympathetic, then what's going to happen? First choose from these two, then as a result, choose from these two, then as a result of that, choose from these two. So for number 2, parasympathetic response. First choose from the first two, then the second two, and then the third two. Boom, boom, boom. See if you can do it. So I helped you on the first one. No help on the second one. Let's see if you can do it. Talk to each other if you need help. Okay. So as a result, let me, the whole idea of this lecture is to teach students how blood pressure is affected. How does the parasympathetic system affect blood pressure? Will it go up or down?
Down.
We'll go down. Ultimately, that's it. But this is the physiology to get there. Okay. I put these two first because one of those happens. And I put these two second because they happen as a result of up here. And this happens as a result of that. So it's all, that's the way I'm trying to train your brain to think. The next slide shows you why vasoconstriction or dilation can affect resistance to blood flow. This is the classic fluid flowing through a tube. So what do we understand about this? Let's go with red, symbolizes a blood vessel. Blood flowing through it. Right down the central axis is where you have the best blood flow, the fastest laminar blood flow. The velocity of blood flow will be the fastest right in the middle. In that direction. Now, imagine blood flowing through the whole tube, but subdivide it into layers. So the first layer around the central axis, it will have the fastest velocity of blood flow because it's right in the middle, furthest away from the vessel wall, which provides friction and resists blood flow. And as you get in concentric circles around the centermost layer, say for example, let's call vessel wall, as the figure does, layer 0. So the first layer next to it, call it layer 1, it's closest, so it has the most resistance to blood flow, so it flows slower. But then the next layer, as you go progressively further away from the vessel wall, it becomes faster and faster, right? So that's kind of what we're going with here. This kind of nice, smooth, kind of shape there. And so in terms of constriction and dilation, when you have a vessel that's constricted, you have more layers that are closer to the friction of the vessel wall, so you have an increased resistance to blood flow. If this is in the arterioles, you're keeping more blood in the arteries, you observe an increase in systemic blood pressure. In a dilated state in the arterioles, you decrease the resistance to blood flow. You have more layers of laminar flow away from the friction of the vessel wall. You would observe a decrease in blood pressure because you're letting more blood out of the arteries into the capillaries veins. Right, that's the idea. Now here's to mathematically put it in numbers, for those of you who like that. All other things being equal, if you affect the tube radius by 16%, you down it from 5 to 4.2, you decrease flow by half. Reducing vessel radius by 16% decreases flow by half. That's a lot. So you affect it a little, affect radius a little, affect flow a lot. So that's why I left this up there. So on this slide is an example of radius affecting resistance to blood flow to the 4th power. All right, so let's talk about it in physiology terms of the human body from a localized standpoint and a systemic standpoint. All right, so the first one, your book describes it as a localized intrinsic autoregulatory mechanism. Localized meaning just one part, one capillary bed, one small region. Intrinsic. This operation happens all within itself. There's no external hormone or nerve that needs to make it happen. It's all intrinsic. So, autoregulatory. It self-propagates. Autoreg mechanism. Yeah, the basic idea here is you want to prevent ischemia. You want to prevent hypoxia. Ischemia is a lack of blood flow, so you want to prevent that. Lack of blood flow. Because if you have a lack of blood flow, that will cause hypoxia, which is a lack of oxygen. But the two are connected. If you have a lack of blood flow, you're going to have hypoxia. They kind of go hand in hand. So you want to prevent these things from happening. So lack of blood flow causes a lack of oxygen for the cells. So if you, like for example, that picture I show you, if you have an artery giving rise to a small arterial, I'll just kind of draw the arterial part, and it's supplying blood to cells. If there's plenty of O2, you can't have blood flow to all capillary beds at all times. There's only 5 liters that you're circulating. So frequently, if you have plenty of O2, what you'll do is you'll constrict the arterial response so that those precapillary sphincters are on, and you bypass the capillary bed. Okay. So basically, just stop blood flow. Don't need it. Divert it somewhere else. Okay. This is okay. Of course, over time, oxygen will oxygen levels will start to decrease. And so to prevent hypoxia, this arterial within the endothelium, the metabolite nitric oxide will accumulate. That causes the vessel to vasodilate intrinsically. That will restore the flow. So when you vasodilate, the process is restore flow, okay, because you're vasodilating and you, like I said, you prevent ischemia. Okay, and you can just keep going back and forth to constrict, dilate, all depending upon the metabolic needs of the tissue. It self-regulates, okay? And so I guess nitric oxide is the one molecule to know that helps that process happen. There are others. I'm just giving you one to know. There's a good figure that kind of shows it better than the one I had there. I think it's 19.4 on the newest edition. Yeah, it's on page 712. In the latest edition. Well, I drew this, but they draw it much better, you know. But that's the concept there. That happens all intrinsically, all the time, in every part of your body. Now, there are other things systemically that happen where it's widespread. Extrinsic. It's a sympathetic response, so it's happening systemically throughout the whole body because you have blood vessels everywhere. This is the fight or flight response. This is, for example, in our lab Friday, the painful stimulus that causes an increase in blood pressure. It's how your body responds to stimuli. Now, you have a large group of blood vessels that supply blood to your digestive tract. And during a fight or flight response, you don't use that, so you constrict it. So I'll draw, like, say, 3 blood vessels representing arterioles supplying blood to GI tract and liver. But like I said, not using that so much in the sympathetic response. So sympathetic nerves will constrict those arterioles, and you'll decrease blood flow to those areas. You'll increase resistance, decrease blood flow to this large group. Increase capital R. What you're doing is you're going to divert blood to a smaller group of arterioles that are the working muscle beds for your fight or flight response. So I'll draw one vessel with a smaller group, skeletal muscle. And also vital organs. Vital organs are brain, heart, lungs. Now, so those will vasodilate. So I'll kind of draw this like just a little bigger, right? So you increase the blood flow to where you need it. However, because the larger group is constricting, if you were to measure blood pressure, you would observe an increase in blood pressure when you take the measurement while you're in pain. So, like I said, the subject not a painful stimulus, you're measuring blood pressure while their hand is submerged. Not after they take it out, while they're submerged. Some students make that mistake in protocol. So observe an increase in systemic blood pressure. So to sum up, the sympathetic input to arterials elicits a vasoconstrictor response very well with the GI tract and liver. Sympathetic input to working muscle beds, that's a smaller group, it's more of a vasodilator response. Like you're shunning the blood to where you need it. Overall, you see a jump in blood pressure. So that's how the arterioles respond. Now the veins respond differently. I want to make sure you understand how the arterioles respond. You clamp down, increase resistance. That's the basic idea. So venules and small veins, they increase venous return during a sympathetic response. And I call it the mobilization of the blood reservoir. Basically what you're doing is you're taking the entire blood reservoir and you're shrinking the container just a little bit. So there's a difference between the arteries and the veins here. So let me clear the board here and explain that. So for arteries, let me see what I got here. So arterioles. So what I'm saying is the sympathetic efferents, they clamp down in one location. And at that location, you're restricting the radius. Therefore, you see an increase in capital R. However, this concept does not carry over to veins. For veins, the bigger, you're not clamping down on one part. You're just taking the whole tube and just shrinking it just a little bit, say like just that much. And you're doing it not at one location, but over the entire length of the tube, say, a larger area. So you affect a larger cross-sectional area, but less so. So I'll say, for veins, you have a slight decrease in little r, but over a larger area. Overall, what we see is there's no effect on the resistance to blood flow. You don't want that. You actually want to increase the venous pressures. No effect on capital R resistance. What you're really doing is you're decreasing the capacitance. Decrease capacitance. So when you do that, you're shrinking the whole container, you're increasing the venous pressure, which is unusual. Increase venous pressure. Increase venous return. Increase cardiac output. Because why? Boom, boom. More in, more out. Frank Starling. So that's the chain of thought you need to have for veins. all of your blood, not all of your blood, most of your blood is sitting in your veins, right? It's called the capacitance vessels, the blood reservoir. So that's why I titled this slide, the mobilization of the blood reservoir, this phenomenon. Because what are you doing? Well, if you're increasing venous return, it's got nowhere to go but to the other side, right? It's all sitting in the veins. In the sympathetic response, you want to get your heart pumping and get more blood to the arterial side to boost the blood pressure so you can divert blood to the working muscles. So let me read what I have on my slide, restated these concepts here. Refer to this slide again and again if you have to, if you're not getting it now. So sympathetic stimulation, the venules and small veins, it generates a small constriction over a large cross-sectional area. Change in radius affects capacitance in venules and small veins with no effect on resistance. Okay. Changes in capacitance rather than resistance occur because the large cross-sectional area is affected. So, I remember being confused as a student because I had this down. But then he's like, I don't get it. You said you decrease R, but you don't affect big R? And so he gave me this analogy here where you're not just clamped. It's like he gave me a garden hose example. Like if you ever have a kink in your garden hose, you turn the garden hose on and no water comes out, so you have to pull the garden hose out and look for the kink, right? Because that's like this. No blood's flowing, okay? No water's coming out. But then he said, okay, what if you just take the whole garden hose and just replace it with the garden hose that's just this much smaller? Well, that's not going to stop the flow. In fact, it's going to increase it, right? If you have that visual in your mind. That's what's going on here. You're increasing the return to the heart. So, underline your main points here. Boom. Ultimately, increase the inflow. Increased cardiac output is increased inflow into the arteries. What are you doing here? When you increase the inflow there, over here, when you increase the resistance, you're decreasing the outflow. That's what I have on the slide. Can you see that? Increase the resistance, increase the outflow. So, for a little diagram, more in, less out. What do you expect to measure? Increase in blood pressure. All right, here's a picture showing that sympathetics affects the artery side as well as the vein side. So to sum up, I have 1, 2, 3, 4 here. You influence the inflow, you influence the outflow, you vasoconstrict here. 1, 2, and 3 cause 4. The whole point of the lecture is to teach students the physiology of how blood vessels can maintain arterial pressure. So, let's put it this way. Well, let's just look at this slide. Look at that equation. Blood pressure as a function of cardiac output and resistance. It's all about the pressure. Blood pressure, cardiac output, peripheral resistance, R. Cardiac output is influenced by heart rate times stroke volume. That's cardiac output. In this lecture, I've been calling it the inflow. The general idea is, if you increase cardiac output, you increase blood pressure. Usually the two go hand in hand. If you see an increase in cardiac output, you will also observe an increase in peripheral resistance caused by a vasoconstriction. That's the number one way you cause an increase in overall peripheral resistance. Okay, so what's the mechanism to cause these things to go down? Vasodilation, a decrease in heart rate, a decrease in contractility of the heart. Okay, that would cause a drop in cardiac output, a drop in peripheral resistance, and a drop in blood pressure. So all the arrows either go down or all the arrows either go up. And it's important to understand things on the right cause the change on the left. Now that's the basic idea. So when you read your handout for your Friday's lab, I made copies for you, by the way. If you didn't print it out, I'll let you pick it up later. I want to talk about a different topic, the venous pressures. I'm going to change gears. And I want to circle back and talk about veins because they're our pressure reservoir. But, well, most every day when things are normal, venous pressures are very low. So the question I want to present in this lecture is, how do veins accomplish venous return when there's no pressure in them? How do veins accomplish venous return? Return to where? The heart, yeah. So how do veins accomplish venous return with no pressure? They're too far away from the heart. Those arteries, capillaries, then there's a huge drop off in pressure. There's not enough pressure to push blood back to the heart after the capillary exchange. So there are other things that are compensations. One thing is a structural observation that we made. They have large lumens, but they also have valves, and there's a couple of venous pumps I'll define. So here's an illustration to show you the large lumens. Number one. Veins have large lumens. So what we learned today is that there's less decreased R, right? Decreased resistance to blood flow. So that helps. There's no pressure, so there's less resistance for blood to flow. But that's not enough. You got to move the blood, even though there's less resistance. And so this shows what happens when you squeeze a tube full of fluid. What happens with and without valves, with and without muscles squeezing the tubes. If you just squeeze generic tube and there's no valves in it, right here, you're squeezing blood or fluid up and down. Let's say you don't squeeze the tube, but you have valves. Well, at least you prevent blood from flowing backwards. Okay. So this is how it really works. You got the valves in conjunction with contracting muscles. So when you squeeze this middle compartment, blood is prevented from going to the previous compartment, and it's only squirted forward, back towards the heart. So number two. Venous valves. I said prior, they're like SL valves. They prevent this backward flow of blood. They work in conjunction. With muscle. It's called the skeletal muscle pump. It doesn't have the heart pump, but your other muscles throughout your body contract, move. So that's why it helps to get up during a long flight to help circulation. Things like that. This shows the skeletal muscle pump in more nuanced detail. I mean, just like the heart, the ventricles have to fill with blood before they can pump blood. So prior to a muscle contracting, this middle compartment is receiving blood. Then when you squeeze, you push the blood forward. And then when the muscle relaxes, it has to refill. So that's what this is showing you in a stepwise procedure. You squeeze, refill, and that helps the venous return. The other pump is a respiratory pump, which depends on the respiratory activity of just simple breathing. When you take a breath in, you expand your chest cage a little bit. Your thoracic volume increases. When you increase the volume, you decrease the pressure ever so slightly compared to atmospheric pressure. So in the chest region, and of course, also notice, are you standing up or lying down? This person is lying down. What do you eliminate? Which pressure? There's three. Hydrostatic, driving pressure, transmural pressure. Which one of those is eliminated from gravity? The hydrostatic pressure. You lie down, you eliminate the hydrostatic pressure. That helps. Take deep breaths, lie down. A little bit negative pressure. Everywhere else in the body, it's the pressure on the body is atmospheric pressure. Okay. That creates a slight gradient to draw blood back to the heart because of the breathing activity. So inspiration, a breath in. Okay, you increase thoracic volume. Decrease thoracic pressure. What you're doing is you're creating a slight negative gradient relative to atmospheric pressure. Generates a slight negative pressure gradient relative to atmospheric pressure. Helps venous return. So they call that the respiratory pump, quote unquote respiratory pump. Now that concludes the slides, the lecture slides for here. I do have practice questions, and make a note to yourself. I just threw all these at the end. They're kind of like study guide review questions. You can go back and look at these yourself when you feel you've spent enough time studying the material. And it's a good check for understanding. It goes all the way up to 13 there. To get you ready for Friday's lab, I want to teach the baroreceptor reflex. That's right here. So we're still talking about blood pressure. So Friday's lab is a blood pressure physiology lab. So I had mentioned the cold pressor test. I also mentioned that, well, maybe I didn't mention it, but what you'll see is that you'll also have to lie down in this lab. It might help to bring an exercise mat or something to have your subject lie down, and we will be taking blood pressure measurements. You know, something I like to talk about that we can't do in lab, obviously, is talk about hemorrhagic shock, which is bleeding. Bleeding, or the fancy way they put it, percentage of total blood removed. Well, anyways, this is over a time course of about a half an hour. And loss of blood on the x-axis, percent normal cardiac output and the arterial pressure, y-axis. Could lead to shock. So shock is a lack of blood flow, just blood stops circulating. And so I like to kind of address this. This is kind of why we emphasize how important it is that the body is well tuned to maintain or increase blood pressure. So something you may not notice is, look at the arterial pressure. As you start to lose blood from 0, you're actually able to maintain arterial pressure all the way up to about 20% blood loss. And so 20% blood loss, so how much blood is there? What's the blood volume? I've been saying it. About 5 liters. So what's 20% of 5 liters? 1 liter? Now, how much is in a typical water bottle? About ½ liter? So imagine 2 of these is 1 liter. I've always thought, people say, you've lost a lot of blood. Well, how do you know? What's a lot? Well, according to these data, 1 liter is. Because after you use about 1 liter, your blood pressure starts to plummet, and that's shock. And so imagine if you're a first responder, you want to estimate the blood loss. I don't know, they'll probably give you other tips. Imagine 2 bottles full of blood just dumped all over the place. What would that look like? I'm not sure. But that's a lot of blood. You see that much, it's like, okay, they're probably, if they lost that much blood, they're probably unconscious. But we call this remarkable ability to maintain blood pressure while losing blood the first plateau from 0 to 20. So from 0 to 20% blood loss is called the first plateau, where arterial pressure is not affected. No drop in arterial BP. So this emphasizes the value of the sympathetic reflexes. Those 3 things. Number 1, heart rate max. Okay, your pulse is going. Maybe 180 is a good max. You're going to keep that cardiac output as high as you can for as long as you can. The other thing, the arterioles. Massive arteriolar vasoconstriction, right? You want to keep as much blood in the arterioles, in the arteries that you can. Well, the third thing I mentioned was mobilization of the blood reservoir. That slight vasoconstriction of the veins. All 3 of those are why the body can maintain blood pressure in this first 20% of blood loss. But then ultimately, cardiac output and pressure start to plummet. When you get to around 50% normal, see this little dip here. They call this at 40% blood loss, like the second plateau. What you see there is, at this point, the brain starts to become ischemic, your vital organs. Up until then, this is keeping blood pumping to your vital organs at least. So from here, brain is ischemic. This is like a last-ditch effort to maintain pressure. Hopefully, blood volume can be restored. So, that's why half an hour. That's how long it takes. That's not very long. That's why when you hear the siren, you're supposed to pull over, right? Now let him through. Okay, maintaining arterial pressure. So from a textbook point of view, they break it down. How does the body respond to long-term, short-term stresses? Okay, the slide I just showed you, which was that, long or short? Sure, half an hour. That's real quick. So we're going to learn about the baroreceptor reflex for that. For this one, most of the time, longer term responses, days, weeks, months, is BP is regulated by regulating blood volume. So just to kind of distill it down, over a short term, I'll talk about this reflex response. Over a longer term, hormones that alter blood volume are really good to maintain blood pressure over a long-term stress response. Now that's review actually. I don't know if you remember from test 1, I kept saying this hormone or that hormone, increased water reabsorption, increased blood volume, increased blood pressure, right? Remember that whole thing? Now that is still true for this chapter. And what I did to make it easier for you is I just kind of put this table together to help you study for this test for those hormones. Still got to know them. Well, for the adrenal medulla, this is actually part of the short-term stress response. But epi and norepi are considered hormones that can get your blood pumping, increase cardiac output, increase peripheral resistance, increase blood pressure. Atrial natriuretic peptide, that's the only one that can decrease blood volume, decrease blood pressure if pressure's getting too high. Yeah. Go back and review ADH and EPO and RAS mechanism. All of those acted by increasing the blood volume to increase blood pressure. Okay. So that's over a longer term stress response. What we're talking about now that I haven't talked about before is everything that we've been discussing this morning and last time about the baroreceptor reflex. And so this kind of prepares us for our lab on Friday. So our nervous system can maintain either of these quite well to help increase or decrease blood pressure depending on what the disturbance is. So any reflex response must have a receptor, a mechanism to detect the body, the change in the body, in this case blood pressure. You must have, you got to know your nerves again. There's afferent pathways that send information to the control center. You compare it to some set point. Okay, in our case it's going to be normal blood pressure. And it gets out of whack. You got to immobilize the correct response so that you can affect the correct neural pathways to affect the correct organs to restore the homeostasis set point. So this slide is just outlining the reflex response for the baroreceptor reflex. I'll take you through this right now. So the thing about reflexes is we're going to talk about it both in terms of your lab, a disturbance where you increase the blood pressure and then decrease the blood pressure. So there are safe ways in lab we can increase and decrease blood pressure. I mean, we can't do things like choke you out or bleed you, right? I mean, but there are safe ways that we can operate in the lab. So in this one, the safe way to increase blood pressure is the cold pressor test. I mentioned it before. Whenever you see the word pressor in physiology, that means increase in blood pressure. Submerge your hand in cold water. It's very painful. It's a noxious stimuli. Blood pressure will get out of whack. The pain will cause an increase in blood pressure. And I don't want you to be scared. I mean, it is painful. My daughter used to go to this sleepover, and they would, for fun, they would do it. They said they would put their ankles and feet in cold water and see who could hold out. We call it the ice bucket test. You should observe this. So what's happening is the painful stimulus, when you get this jump in blood pressure, what's happening is at the carotid sinus and the aortic arch, the baroreceptor is picking up. Baroreceptor. At some point, I should have mentioned that the baroreceptor, there's two locations, Carotid sinus, aortic arch. Those two spots. That's where they are, close to the heart. What's happening is they're detecting a change, an increase in the transmural pressure. I'll just put P-trans for short. What's happening is the stretch is increasing, right? And the nerve ending is in the vessel wall. So it can detect that stretch across the vessel wall. Increased stretch. It's a mechanoreceptor. And so it'll respond by firing faster when you squeeze it. So maybe everything's all good, just fire at this rate, but then the painful stimulus comes along and you fire more. So those increased amount of action potentials, that increased AP frequency, I'll just say increased APs, you send that to the brain via a branch of cranial nerve 9, glossopharyngeal. In the medulla, there's a cardiovascular center that helps regulate blood pressure. Now there are 3 subcenters that are outlined there. Cardioinhibitory, cardioacceleratory, vasomotor. Those are the 3 that we need to discuss. Cardioinhibitory. Cardio acceleratory. This is kind of where I always remind myself, what's going on? Oh, blood pressure's too high, I want to lower it. This is what's happening. Okay, oh, painful stimulus, boom, increased firing. Okay, what's the correct response? I compare this input, more APs. What's the correct output? I got a lower blood pressure. So this is where I want to turn on parasympathetic. I want to block sympathetic. Turn on parasym, block sympathetic. SYM. That's the idea. So with these centers, what you do is, okay, well, let's turn it on. Let's turn on this one, cardioinhibitory, off, off. Those second 2, cardioacceleratory, vasomotor, they're like sympathetic things. Just turn them off. Okay. So the result of that will be here to affect the heart. You're going to decrease sympathetic impulses to that. You know, there's the vagus nerve. The vagus nerve. Cranial nerve 10. Vagus nerve. Affect the heart. Decrease heart rate. Decrease contractility. Decrease cardiac output. Okay, that's how the heart's affected. Now, these other ones, you're not using cardioacceleratory in this one. Vasomotor, you're basically turning down the sympathetic tone. You're just decreasing tone. Decrease SYM tone. So what happens is those blood vessels will become more vasodilated. I'll just put VD for vasodilation. So overall, when you vasodilate, you're decreasing, I know it's getting crowded here, resistance. So let me kind of circle that in red. The important points here are this and this. And then to make sure I did it right, I always write the equation. Blood pressure is a function of cardiac output times resistance, and I just make sure I did it right. I explained everything that decrease, and that causes a decrease in blood pressure to restore the set point. Okay, so that's what's being explained by this figure. Okay, any questions on this whole reflex thing? I might take some rehearsal, but any questions for clarification? Okay, so in lab, what's causing this imbalance? The cold. I'm going to put out big bolts of ice. You guys just add water, make it nice and slushy. It's supposed to be 5 degrees centigrade. I mean, I'm not going to pass out thermometers. Just cold slushy, that's about 5 degrees. What does water freeze at? 0. So cold slushy water is about like 5 degrees centigrade. So that's that part of the lab. The other part of the lab is we have to induce a drop in blood pressure. Now you guys already did that where you lie down and you sat up. For this one on Friday, it's going to have a stronger effect if you lie down and then stand up. It's called orthostatic hypotension. Tell you what, let's tackle that after break. Come back in 15 minutes. So really that's 20 minutes, right?
Yeah.
That's more like 25.
Yeah, all right. Well, no one ever complained about that, so it is what it is.
I know we have the cadaver presentation. It's only 1 day presentation, or is it?
1 day. 1 day.
It's like a group presentation?
I'll present to 3 different groups.
Okay. So there's no, you can't leave class early or anything today? Because I have a plan to leave town that day.
You know, for that one, I usually provide an alternative assignment where you don't have to come to class. Some students have a problem with that. Like you might pass out or something.